Hello, and thanks for joining us today for the latest Technology Networks webinar, Build Up Your Protein Formulation Toolbox with Uncle. I'm Caroline Clark, conference producer for Technology Networks, and I'm here to moderate today's event. I'm pleased to have Dr. Kevin Lance joining us today as your presenter. A warm welcome to you, Kevin. Kevin is the marketing manager covering the global analytical instrument portfolio at Unchained Labs. His expertise covers biophysical characterization of proteins, nucleic acids, viral vectors, and lipid nanoparticles. Prior to Unchained Labs, his research expertise and experience covered the fields of sustained antibody delivery and nanotechnology. He earned his PhD in bioengineering through the Bioengineering Graduate Program, jointly offered by UCSF and the University of California, Berkeley. Following the webinar, we will have a Q&A session and we will welcome any questions that you may have. You can submit questions for the Q&A session at any time during the presentation. To ask a question, you should enter your question into the box on the right-hand side of the screen and click Send. We will answer as many as possible during the time available. For any questions we don't have time to get to, we will be sure you are contacted offline with an answer. If you experience any technical issues, please click the chat icon in the bottom right corner to request support. Please remember, you can ask questions at any time, even whilst watching the webinar on demand. So without further ado, I will now hand over to Dr. Lance.
Thanks everyone for joining my talk on how to build up your protein formulation toolbox with Uncle. When you think about most tools in the lab, a lot of them look like this. Maybe they're not a pocket knife, but they likely do one thing really well, and you might get one additional functionality out of it. The way that I think about Uncle is shown on the right. It's got a lot of different tools, a lot of different features, and it really helps you solve a lot of problems. Today, this talk will focus on formulation problems, and we'll look at how a small slice of 5 or 6 tools from Uncle help you solve those interesting and everyday challenges in biologics formulation. With that, I'll introduce Uncle. It's a combination of 3 different detection methods, all built into one instrument. We have full spectrum fluorescence, which excites with one of our 2 lasers, either a 266 nanometer UV laser or a 473 nanometer blue laser. And Uncle will read full spectrum fluorescence coming out of that experiment to give you the whole picture of what's going on with your sample. For proteins, you can use intrinsic fluorescence to read the fluorescence of tryptophan and tyrosine residues. Or if you have challenging samples or other unique questions, you could add labels and dyes and monitor their fluorescence. SLS is static light scattering. That's going to be the intensity of the light from the UV and blue lasers that bounces out of the samples. Because that laser is hitting particles and bouncing back out, SLS is a really great method to look at when particle formation is occurring in a sample. We'll check out some of the advantages of SLS versus other techniques during this talk. DLS, or dynamic light scattering, is Uncle's 3rd detection method, and it lets you really crank up the detail on sizing and size distribution of your protein sample. Besides gathering size data, DLS is powerful for understanding what's in your sample, and it can be used to quality check proteins before you start an experiment. For example, for an antibody, you might see a nice monomer peak at about 10 nanometers in diameter, but you could also look for extra aggregates floating around in the 100 to 250 nanometer diameter range. Starting with those 3 detection technologies and add the ability to control the temperature of your sample from 15 to 95 degrees Celsius, and you could use thermal ramps to stress out your samples to see which ones unfold and start to aggregate first. Or you can do isothermal experiments and hold things at elevated temperatures over long periods of time. Or you could just do quick DLS reads on a small sample volume at room temperature. Uncle can do all of this and more, and that's why it's really the all-in-one biologics characterization platform. Combine those 3 detection technologies, and you get a long list of over a dozen applications that help you solve a wide variety of stability and characterization problems. Today, we'll be focusing on applications relevant to protein formulation and stability, so that'll be applications like TMT-Ag, TMS-Cypro, isothermal stability, KD, B22, and G22, and sizing from DLS as well. However, this wide variety of applications can solve problems from formulation work to lead optimization to capsid engineering for viral vectors. The sort of magic secret of Uncle is the uni. It's an anodized aluminum frame with 16 quartz cuvettes, where each quartz cuvette holds 9 microliters of sample. All you do is pipette in your 9 microliters and seal the uni inside of its blue frame so the silicone seals clip around the quartz cuvettes. Just like that, you have a nicely sealed sample where you don't have to worry about evaporation over long periods of time or over a thermal ramp. This is also a handy sample holder because you can pop it right into a 37-degree incubator and do a weeks or months-long stability experiment right in the uni, or you can put it into a freezer and go through freeze-thaw cycles also right in the uni. Those are the advantages of having a well-sealed sample holder that needs such a small sample volume. Once you have a sealed uni, the next steps from there are pretty simple. The Uncle's door opens up, you remove the sample cover, load the uni and its blue frame onto the copper-colored Peltier heating element, put the cover back on, and then you're done. The uni slides into the Uncle, and everything else is taken care of through the software. Here's what the raw data of an Uncle experiment looks like. Over a heat ramp, Uncle will excite and read the full spectrum fluorescence of a protein sample at numerous temperatures. Each line in this graph is a fluorescence read of a protein excited with the 266 nanometer laser, starting with a read at 15 degrees Celsius and going all the way to 95 degrees. You can see by following the curves from top to bottom how they shift to the right side of this graph, which are the longer wavelengths. This phenomenon is called a redshift and occurs because the protein is unfolding. Buried tryptophan residues have a shifting fluorescence emission as they move from being buried in hydrophobic pockets to being exposed to an aqueous environment. Uncle analyzes this signal to look for the barycentric mean wavelength, the BCM wavelength, which is the spectral center of mass. That's the wavelength where half the area under the curve is to the left and half the area under the curve is to the right. Because Uncle is looking at many wavelengths, it has robust signal-to-noise ratios and doesn't need to rely on high-frequency measurements other instruments use to offset lower quality, lower signal-to-noise measurements. On this graph, you can also see a prominent peak at 266 nanometers. The area under the curve for that peak is the SLS signal from the UV laser as it hits particles present in the sample and bounces back out. The short wavelength of that SLS laser make it an incredibly sensitive technique for detecting when aggregate formation begins. It will detect changes in molecular weight well before they begin to demonstrate a size change by DLS. Uncle plots the BCM wavelength versus temperature, and I'm showing that data here in blue. Since the blue data is coming from the protein intrinsic fluorescence, it's giving insight into protein unfolding behavior. The redshift behavior is clearly seen as that BCM wavelength increases as temperature increases. At melting temperature 1 and melting temperature 2, the graph shows 2 inflection points. Those will be melting temperatures and unfolding events for the protein. In green is the SLS intensity from the 266 nanometer laser gathered at that exact same time. For this antibody, SLS data remains very flat all the way through TM1 and doesn't show an aggregation onset until paired with TM2. Where that signal increases, Uncle calls a TAG, or aggregation temperature. So in one experiment, we get a simultaneous answer on when this protein starts to unfold and which unfolding event is correlated with aggregation in this sample and buffer. Because Uncle uses full spectrum fluorescence detection, you have a lot of different choices to always see what's happening. On the last 2 slides, we focus on protein intrinsic fluorescence, but we can also look at dye-based fluorescence. In this case, we have a dye that's fluorescing between about 500 and 650 nanometers. That's a great tool to have available if our protein has no intrinsic fluorescence, weak fluorescence, or if our buffer has a component that fluoresces in response to UV, or in a few other cases. Let's check out one example on the next slide. In this case, we have an antibody sample, and it's in the same concentration for all 3 of these graphs. On the left, it's in a standard histidine buffer. In the middle and on the right, we've added 2 excipients. In this case, both excipients are quenching fluorescence, so we don't really have any protein fluorescence data left to rely on to analyze this antibody. Well, how can Uncle solve this problem? Since UNCLE is full spectrum fluorescence, we can use the 473 nanometer blue laser to excite a fluorescent dye and collect emission spectra in the region from 500 to 650 nanometers. In this case, we'll use cypher orange dye so that we're still able to understand the unfolding of a protein using fluorescence that's not going to be quenched by the excipients in our buffer. Here's a snapshot of the results where we have the antibody in its histidine buffer in green and in the excipient buffer, buffer number 1, where we saw fluorescence quenching in blue. In the histidine buffer, the unfolding behavior of this antibody is clearly shown by 2 melting temperatures. However, in buffer 1, those events are completely hidden and we lose the ability to detect those melting temperatures. But with our cypher orange dye-based fluorescence experiment shown on the right, we can now answer the question, how is my protein unfolding? And we see for the antibody a clear shift in our 2 unfolding events to lower temperature. TM1 shifts lower and TM2 also shifts lower. That means that for our excipient, it destabilizes the protein and causes our antibody to unfold at earlier temperatures. This is really helpful because with only intrinsic fluorescence as a tool, we would have had no path to get an answer about what's going on with this excipient and our protein. This approach is a great solution for proteins that have weak fluorescence or no fluorescence, such as the protein shown on the left. We see our SLS peaks, but no protein fluorescence. By adding Cypro, we're again able to see a strong fluorescent signal in the 500 to 600 nanometer region of the spectrum. Analyze the area under the curve for that Cypro orange data, and the denaturation curve shows a clear transition where the melting temperature has been assigned at the peak of the first derivative, which is shown by the red line. Again, we've gone from having no fluorescence to being able to clearly measure protein behavior. Now let's look at a broader story for UNCLE data and how it can help you screen for bad buffer behavior. In this experiment, we're taking an antibody and adding it to 2 simple buffers, a histidine buffer and an acetate buffer. We'll call the histidine buffer the commercial formulation, or CF. In this graph, we have triplicate samples in our commercial formulation, and you can see that the melting temperatures line up extremely well, and we're still getting that 2 melting temperature behavior that we're expecting for this particular antibody. If we buffer exchange that into an acetate buffer for comparison, we'll notice that there's a shift in the signal, and if we quantify that by looking at the melting temperatures, we see that there's a big impact of going into the acetate buffer because both melting temperature 1 and melting temperature 2 have shifted to lower temperatures, meaning the antibody is unfolding more readily in response to thermal stress. Since we know we're gathering simultaneous SLS data with our fluorescence data, we can get an answer not only on unfolding, but also on aggregation. Here we're adding SLS data to the graph, which is indicated by the circular data points. To simplify things, we're looking at just 2 samples to make the colors easier to pick out. In the acetate buffer in purple, the antibody shows very sharp and extreme aggregation. We can identify when this peak starts. We know that the slope of this peak is extremely steep, and we know that the SLS signal increases to extremely high levels. So this sample is reaching a second melting temperature and is aggregating extremely rapidly and to large-sized particles. But what about the commercial formulation? Well, from the acetate sample, now we know what really bad aggregation looks like, but we also have some data down here. So how is the antibody behaving in its commercial formulation? Before I zoom in on that SLS data, I want to quickly take a detour to what UNCLE's DLS data can show you. In this case, we have DLS data taken before and after that TMT thermal ramp. And we see an 8.08 nanometer size at the start of the experiment and an 8.17 nanometer size at the end of this experiment. So a 0.09 nanometer change in the diameter for that antibody in a commercial formulation across the thermal ramp. If we keep that small size change in mind and go back and look at the commercial formulation SLS data, we can see that the antibody is still aggregating at melting temperature 2 at its commercial formulation, and the SLS is sensitive enough to pick up on exactly when the aggregation behavior starts. That's pretty impressive when you consider the magnitude of the small size change shown by DLS and the clear change in the SLS signal that you see here. Another nice feature of SLS is that it works across the whole concentration range of uncle, from low concentrations like 0.05 milligram per milliliter, all the way up to extremely high antibody concentrations of hundreds of milligram per milliliter. That means you'll always have aggregation data to pair with fluorescence when you run a TMT-Ag experiment on uncle. SLS is also extremely sensitive for detecting when aggregation begins. In this case, we're running the same thermal ramp twice on the same sample, but in one ramp looking at the SLS signal shown in blue, and in another ramp looking at DLS data shown in green and overlaying them on the same graph. As you can see, SLS is picking up on aggregation first. So this confirms with what we saw in the previous experiment, where SLS easily picked up on what was a minuscule size change for DLS. That SLS sees changes in size more sensitively than DLS. It'll pick up on size changes before DLS does. That's a quick overview of what a simple comparison of two buffers might look like for an antibody. Now let's look at a slightly more complicated experiment where we're focusing on that histidine commercial formulation buffer, but now we're going to add different excipients and do a little excipient screen to start to understand how our antibody is going to react with typical excipients. We have histidine as our base buffer. We'll add sodium chloride, arginine, and sucrose as excipients to evaluate. Also note that I'll be consistent with the colors shown for each buffer, so you can track this across all the different experiments. First, let's look at the results of another TMT-Ag experiment. We see that histidine and sucrose maintain pretty consistent melting temperatures for TM1, but sodium chloride and arginine show a shift to earlier melting temperatures since they destabilize the structure of the protein and unfolding is happening earlier. Interestingly, melting temperature 2 shows very little shift, maybe just a slight destabilization by arginine, but no excipient shows the same shift of several degrees that melting temperature 1 showed for these excipients. If we add on the SLS data on top of that fluorescence result, we can see that with all of these excipients, we're still seeing aggregation occurring in concert with TM2, which is not guaranteed, so it's good to confirm the excipients don't drive a dramatic change in aggregation behavior. And we do see that in this case, we have very, very similar melting temperatures, but sodium chloride and arginine drive rapid and severe aggregation behavior, while histidine and sucrose drive less extreme aggregation behavior in our sample. Now let's peek at another application on uncle called B22 and KD. What we're doing with the B22 and KD experiment is taking a quick room temperature snapshot to see if your protein formulation combination is at risk of aggregation. We'll be seeing if there's non-specific protein-protein interactions going on between the proteins in your formulation, and therefore putting your protein at risk for aggregation. How this experiment works is by running a range of concentrations, typically between about 1 and 10 milligram per mil for an antibody, and comparing either diffusion coefficient or light scattering across the concentration range. For this case, we'll just focus on a KD experiment, so the diffusion coefficient will be our measurement. As concentration increases, we're increasing the frequency of protein-protein interactions in our sample. If diffusion coefficient decreases, that indicates that proteins are behaving like they are larger and the underlying protein-protein interactions are attractive and the protein is at risk for aggregation. The flip side of that is to get a protein with an increasing diffusion coefficient behaving like it's smaller, which would have self-repulsive interactions and be less at risk for aggregation in that formulation. In this case, let's look at the result quickly in a table to compare across the 4 different excipients that we're testing. For KD, histidine and sucrose perform extremely well, so they are showing highly repulsive protein-protein interactions in these 2 buffers. Arginine is quite neutral, and sodium chloride is tending towards aggregation. B22 in this case agrees, although that's not always a guaranteed correlation. All right, so now let's take a look at the isothermal stability application. This is a really handy tool in uncle to monitor aggregation and unfolding across seconds, minutes, hours, or days, up to about a week. So with this kind of experiment, we could be finding or confirming the temperature that we're going to use for a longer term or full-scale isothermal experiment, or we could be using this as a faster way to compare buffers and excipients like I'm doing in this case study. With Uncle's isothermal experiments, we can measure fluorescence and SLS, or DLS, or all three technologies at once. For this result, because the 473 nanometer blue laser hasn't yet been the star of the show, we'll look at the SLS intensity for that laser. What we see agrees with the aggregation behavior that we've seen so far, which is that sodium chloride has the fastest rate of SLS intensity increase, indicating that aggregation is starting and proceeding faster in that sodium chloride sample. Arginine is a little bit behind that, and it's aggregating not quite as fast. And histidine and sodium chloride show very little aggregation. So now you know that if you're running a longer term isothermal experiment and setting the temperature quite high, 60 degrees Celsius, that might still be acceptable for your histidine and sucrose samples, but you can expect to see aggregation in your sodium chloride and arginine samples. Our last application is going to be looking at G22, which is also known as the Kirkwood-Buff integral. G22 takes a look at how our protein interacts with itself in a more crowded solution. So B22 is for a more dilute solution up to about a maximum of, say, 10 or 20 milligram per milliliter. But G22 works best at concentrations that are much higher, from 50 milligram per milliliter all the way up to 100 milligram per milliliter and beyond. Positive values of G22 indicate undesirable, attractive protein-protein interactions. Negative values of G22 indicate preferable, repulsive protein-protein interactions for those highly concentrated protein formulations. If we check out our 4 different samples in the G22 application, we see a really interesting result that tells us there's more to the story. At these concentrations, from 50 up to 100 milligram per mil, we can see that the histidine and sucrose buffers have slightly negative values, while our dark horse candidates of arginine and sodium chloride show larger negative G22 values. This indicates arginine and sodium chloride are actually helping prevent aggregation in these higher concentration formulations. A pretty interesting counterintuitive result that we would have missed if we didn't check things out with the G22 application. So when concentrations increase to more dramatic levels along the lines of a final concentration of a drug product, testing things out with G22 is worthwhile to see what helps inhibit aggregation by promoting repulsive protein-protein interactions. Okay, so if we were doing this for a living, what would we do next? What choices would we make? Well, the first question is, what concentration do we really care about? If this is an antibody critical reagent destined for an ELISA, you may be more interested in lower concentration behaviors. If it's a drug substance headed for an injectable formulation, you would put more stock into data gathered at higher concentrations. If we're operating at lower concentrations, we may favor histidine and sucrose in our formulation buffer, because those are the ones that perform best at lower concentrations to stabilize protein and prevent aggregation. But if we're targeting a much higher concentration, then we might need to include something like sodium chloride in our final formulation, because it was really the star of the show when it came to a G22 result. So your next experiment on Uncle, after this initial formulation screen, might be to create a DOE to really fine-tune and optimize a formulation buffer based on the specific problems you're faced with. That is our look today at how Uncle's many tools can help you evaluate different formulations and excipients, and how its tools can help you look at protein stability overall, as we saw melting temperature shifts in proteins, both with and without dyes. With that full spectrum fluorescence, Uncle can even offer tools to look at other interesting problems like viral vector stability as well. With Uncle as your all-in-one protein stability toolbox, you get a lot of different applications that mean you can solve the protein problems that you have today and be ready for the problems that you're going to have in months or years from now in your lab. Now I'll pause and see what questions we have.
Thank you very much, Kevin. I'm sure you'll agree today that that was a really great presentation. And we'll now begin the Q&A session. To submit a question to Kevin, you should enter your question into the box on the right-hand side of your screen and click send. We'll answer as many questions as possible during the time available. We've had a few questions submitted already, so I'll move straight on to these. So your first question, Kevin, is, does your instrument measure fluorescence and SLS at the same time, or is it one after the other? What benefit do you get from it?
Hello, everybody. So yes, the Uncle measures fluorescence and SLS at the exact same time. They're measured on the same spectrophotometer. And the benefit of this is that you're able to very uniquely pair up both protein unfolding and protein aggregation information at the same time. So that's very helpful because SLS is going to respond to molecular weight changes in your protein and be incredibly sensitive to aggregation. So gathering this information all at once helps you always understand for that particular snapshot and moment in time what's going on both fronts, both the unfolding and aggregation fronts.
That's great. Thank you, Kevin. Your next question is, can the Uncle sample holder be used for long-term isothermal studies? Any evaporation concerns and any chemical compatibility issues?
Okay, so we call the Uncle sample holder the uni, and it definitely can be used for long-term isothermal studies. Actually, in the Uncle, you can run an experiment up to about a week. And outside of the Uncle, you can take your uni that's sealed in its blue frame with silicone gaskets and pop that into an incubator and do even longer term studies there, removing it to measure each time point. So yep, having the silicone seals on either side of that uni really help keep it sealed for those isothermal studies. The second part of that was chemical compatibility. So the only materials that'll be touching the sample are quartz and silicone, which are both known to be extremely inert for pretty much anything going on in a biologics lab.
That's fantastic. Thank you, Kevin. We have another question. How does the change in pH or the addition of various excipients impact your signal? Would a ratio of 350 to 330 be sufficient?
Okay. So change in pH, typically you will see an impact on stability based on that. So that'll be something that you use Uncle to measure the actual physical behavioral change. And it doesn't really, I would say, impact fluorescence directly, but it does have an impact on the result that you're getting. So optimizing for pH is definitely one of the problems that Uncle can help you solve when you're trying to optimize a formulation. The reason why 350 to 330 ratio isn't always sufficient is, like I showed in a few examples in my talk, is that you can have situations where your buffer can quench fluorescence, or your buffer could absorb those ratios, or your buffer actually could be fluorescent itself. And so if you're only observing those ratios, you're going to, say totally miss if your buffer has fluorescence. You just won't see it as part of the something that you can extract out from your sample. And so it's going to be convoluted in there and sort of give you wrong answers. So having that full spectrum fluorescence gives you extra tools to explore situations when you have buffer fluorescence or quenching, or when you just really maybe want to use a dye to solve a different kind of problem.
Fabulous, thank you. Your next question is, what are the most popular applications for formulation screening?
Okay, so the ones that I covered today are quite popular. I know the TM-TAG application is by far the most commonly used application since it directly studies both protein unfolding and aggregation. In addition to that, isothermal studies are really, really convenient for giving you a quick tool to help explore the design space for larger, longer term formulation studies, because nobody wants to start a 6-month isothermal stability study and then find out at your second time point that aggregation has already started in all your samples. You won't be able to differentiate your samples. So that's why isothermal and Uncle is used particularly often. And then KDB22 are used for looking at aggregation propensity right now without having to do any sort of weight. It's a 30-minute experiment and very convenient. And similarly with G22, it's another one of those give me an answer right now type of experiments for doing formulation work.
Fabulous, thank you. And we've got another question here, and it is, can you do the isothermal DLS in addition to fluorescence and SLS?
Yes. So you can choose if you want to do just fluorescence and SLS, you can choose that. If you want to do just DLS, you can choose that. But more and more commonly, our customers are using all of those techniques at the same time over the course of an isothermal experiment.
Thank you. And we've got time for one more question. So it's, can this be used in a 21 CFR Part 11 environment?
Yes. So we have software tools that can enable, activating 21 CFR compliant features on Uncle. Absolutely.
Thank you, Kevin. I'm afraid that's all we've got time for today. Just to remind everybody, any questions that we didn't have time to get to will be answered offline as soon as possible. You can continue to ask questions even when watching this webinar on demand. A certificate of attendance is available to download from the Handouts tab on the right-hand side of the webinar platform. The webinar will now be made available on demand, so if you do have any friends or colleagues that you think may be interested in watching, please feel free to share the link. Thanks again for your time.